Let me get this thing going again. Like I said, we're doing sling tensions today. And if you have any questions, you should have a Q&A button on your control panel. You're welcome to type in any questions. I do have, if I can't answer the question online, what I can do is either do it verbally, or if we have to, or it doesn't pertain to what we're talking about, I do have somebody helping me out today who can type in answers to you, and so we can keep going. We're going to try to stay on a pretty tight schedule. Like I said, we try to keep this about a half an hour. Like I said, my name is Steve Dewey. I'm the president and general manager of All Lifts Incorporated. And if you'd like to, you can jot down my email address. If you have questions after the session's over, feel free to contact us. And at any one of the numbers listed below. And also, we have a website. This website is still under construction. We're redoing the entire website, but there's going to be a lot of information up there. And I am recording these webinars. One of them is already posted at our YouTube channel, Building and Breaking Things. It is the sling inspection webinar we did a few weeks ago. And I've got another one going up there on load securement, should be going up there probably today. And so you should be able to look for this one also. When we start talking about sling tensions, there are certain things you need to be aware of. You'll see this is the card number 15 out of Crosby's Pocket Guide. And what they do is they list out operating practices. You'll see it says ASME B30.9. ASME is American Society of Mechanical Engineers. B30.9 is the standard that covers slings. And it shows these 12 little practices. We're not going to go through all these practices. The one we're focusing on today is the number 4. The rate of load of the sling shall not be exceeded. And this is the one that people can easily violate just by not doing things correctly. And so you're going to get slings and buy slings, and all slings have to have a tag on them. On this tag will be the vertical capacity, the choker capacity, and you'll see it says V basket, which is the vertical basket capacity. Vertical is just a straight up and down where the total weight of the load is directly on the sling. With choker, there's various ways of doing a choker hitch, either with one eye going through the other around the load, or using a shackle. You'll notice how we've got the shackle pin is through the eye, so we don't put the shackle on the body because you can actually rotate that pin out, or with what we call a traveling hook. And the traveling hook, this is a specialty hook just for choking. But you'll notice that the capacity of the sling drops by 75% when you use it in choke. The last one is the basket, vertical basket. And you'll notice in the vertical basket, both legs are straight up and down. In this case, you end up doubling the capacity of the sling and basket, but as soon as you bring those two eyes together and form this sling at an angle, the capacities are going to change. And you as the rigger have got to be aware of those capacity changes depending on how you're using the sling. When we do use two slings together, and what we would call a symmetrical load, and we define a symmetrical load as any load that the center of gravity or its balance point, its center of mass, is equidistant to each pick point. And so with that, we can take and say that each one of these slings is taking half the load. So in this case, it's 5 tons. That since we're both 5 feet away from each pick point from the center of gravity, this sling will be seeing 2.5 tons of vertical capacity, and this will see 2.5 tons of vertical capacity. And it doesn't matter what the shape of the load is. You'll notice how it's a little longer over here, but the distance from the center of gravity to each pick point is the same. That is still going to be a symmetrical load. Now, what happens when we have a symmetrical load, but now we bring the slings together, and now we have them at an angle? Well, what happens now is we're going to increase the forces on the sling. Now, this little box and these scales are part of a kit that we have. We use it as in our more advanced classes where you can actually see what's going to happen. These little load cells read in grams, and will give readings at various angles. Even though the weight of the load is not going to change, the forces on the slings will change. And so if I have a 2,000-pound load, what we have to do is we have to figure out, if it, based on various angles, what loads are on the sling. So you're a 2,000-pound load loaded at 60, 45, or 30 degrees. And the question would be, what is the load on each sling? And the way you're going to get there sorry about that, I didn't want to cough into the microphone. The way you're going to get there, again, we go back to our pocket guides, these little handy pocket guides. And up here in the top, we have the load angle factor. It says L divided by H. And here we have a little diagram where L is the length of the sling and H is the height from the pick point to where it's hooked. And these two, this is where the calculations are coming from. And anybody who remembers a little bit of trigonometry from high school, this is the cosecant of the angle. Little fun fact. And so what we have to do is now we're going to say, okay, what angle is going to be at, and what are my load factors? So with this little pocket guide, we can actually come down here. And the other part of it is that we also have a capacity reduction. So it's not only an increase in the forces on the slings, we can always also say, as I load slings at an angle, I have a reduced capacity of the sling. And this is the sine of the angle. So at 0 degrees or vertical, we have a 1 factor. So if the sling is seeing 1,000 pounds of load, then it's going to be 1,000 pounds of vertical force. At 60 degrees, you'll see we have approximately a 15%, 13 to 15% reduction in the sling capacity. I always remember it's 15%. It's easier to do the math. At 45 degrees, we have a 30% reduction. And at 30 degrees, we have a 50% reduction. And like I said before, we look at the load factor at 90 degrees, we're increasing the loads by a factor of over almost 16% at 60 degrees, 40%, over 40% at 45 degrees, and we're doubling the forces on the sling at 30 degrees. And if you want to try this out, I know it's after a long weekend, so you're probably going to have to go to the store and restock your beer. So what you want to do is take your 2 30-packs of beer, one in each hand, and walk through the store hanging them straight down at your side. Then try to hold those out away from your body. And you'll feel your arm, how hard you're going to have to work to hold them out there. Well, that's exactly what's going on with these slings. So we have this increase in forces based on those angles, and you're going to find it harder and harder to do it. Well, that's the same thing the slings are going to do. It's harder for them to hold that load out there. And so we have an increase in those forces. So if you want to take and do the math, the first question is going to be, okay, what is the vertical share of the load on each sling? In this case, what are the loads on the sling? So first thing we have to know is, what is the vertical share of the load? Well, this total little piece weighs 2,000 pounds. I've got 2 slings picking it up, and it's a symmetrical load. That means our vertical share is the same on each sling, or 1,000 pounds each. So with 1,000 pounds of vertical share, what is the forces on the slings based on these various angles? So what we'd have to do is say, okay, at 60 degrees, my load angle factor is 1.155. So it's 1,000 pounds times 1.155. This sling is seeing 1,155 pounds of force, and so is this sling, since it's symmetrical load. Now at 45 degrees, we go to 1.414, 1,414 pounds of force. And at 30 degrees, it goes to a 2 multiplier, 2,000 pounds of force. So you can see, just by changing the angles, you can get yourself in trouble. So what we tell people is, that little tag on that sling that I just showed you, that tag has absolutely nothing to do with how much weight you can lift. That tag is actually telling you what's the maximum force that you can put on these slings. And those forces will change depending on those angles that you're using. And so you've got to do the math. Now, this is a symmetrical load. What happens when we go to a non-symmetrical load, where one side is seeing a greater share of the load? Well, now you've got to figure out, okay, what share of the load is over here, what share of the load is over here. And since the center of gravity is closer to one leg, this leg will be seeing a greater share. But how do you know how much? Well, what we can do is we can calculate that out. If we know this is, or suspect the center of gravity is right here, we can measure from the center of gravity to the pick point on this side, from the center of gravity to the measurement on this side. We want to know what this sling is. Well, it's what they call an inverse proportion calculation. We're just saying we're going to use the opposite side. So we're going to come over here. We're going to say it's at 2 foot, and at 2 foot, divided by the total distance of 8 plus 2 is 10. So 2 divided by 10 is 20%, or 0.2. 20% of 5 tons, which is my total weight, says that this sling is seeing 1 ton of vertical force, where here we have 8 foot divided by 10 is getting 80% of the share of the load. 0.8 times 5 ton is 4 ton. This sling is seeing 4 ton share of the load. And so in this case, now we know what share of the load. So now with knowing what share loads, then we have to work out if we're loading them at angles. So we have, as part of our classroom, we have these little boxes. And again, now we can do calculations and determine what share of the load is on each sling. And then also what the angular forces are on the sling. So as part of a workshop, we could actually measure out and say that this, from this pick point here to our center of gravity, is 1.5 feet in scale. And from this one over here is at 6 feet. So my total distance is 7.5 feet. So by running the math through, we can actually determine, based on this whole box weighing approximately 10,000 pounds, what the shear load on each side is and what the angular forces are. And it all comes back to using this these formulas. This formula down here does all of that. It does your inverse proportion calculation, and then also your L over H calculation, all in one fell swoop. So if you get to the point where you have these oddball non-symmetrical loads, or if you're going to drift a load, here we have a load that we're drifting, and you need to know what size chain fall I need on each side to make this pick, we can actually run these numbers through using these formulas. And I'll show you how it works. Here we have an example where we've got a 120-inch leg and a 72-inch leg. Our height is 60 inches. We have a total 5-ton load. It's 104 inches from the pick point to my center of gravity, and from this pick point is 40 inches to center of gravity. Now, these are estimations here, so you may have to run different scenarios. But let's say we think our center of gravity is here, so we want to give ourselves some capability of making adjustments, of being able to move this hook one way or the other to make sure we're rigged to the center of gravity and this load picks level. Every time you pick up something, if that hook is directly over the center of gravity, it will pick level. If this is off a little bit, say the center of gravity is over here, we need to get the hook moved over here, we may have to shorten this sling up to do so. So now when we do this, we have to do some calculations in multiple configurations to determine what size sling, or let's say we're going to change this out and make it into a chain fall we're going to put here, what size chain fall we would need to have. So those formulas on that pocket guide will actually do this for you. If we have the tension in sling 1, which is our left sling on this side, you notice this diagram, the short side is over here, this one, the short side is over here. But we read from left to right. As long as you do this the same way every time and follow the same procedures, you'll keep from making an error. You will use the S1 is this side, S2 is that side, and we're going to fill this information in. So we need to know what the load is. Our load is 5 ton. We have an S1 of 120 inches long. Our sling is 120. 72 inches on S2, D1 is 104, D2 is 40. And all we have to do is, or our height, forgot about our height, is 60. All we have to do is plug this into our formula. And the tension of sling 1 is equal to the load of 5 ton times 40 of D2 times S1, which is 120, divided by my height of 60, and in parentheses, 104 plus 40. Now, I know a lot of you are like me, you've been out of school a long time, and you sit here and go, well, I don't remember how to do this, but what you can do is, you guys may remember, please excuse my dear Aunt Sally. It's your order of operations. So we want to do what's in parentheses first. And in some cases, you may have to go back and kind of refresh yourself to make sure you follow the proper math formulas and the procedures. So 104 plus 40 is 144. 60 times 144 is 8640. My 5 times 40 times 120 is 24,000 divided by 8640, which says that this sling is seeing 2.78 tons of force based on its share of the load, the distance from the center of gravity, and the angular forces that are on here at this point. So it's usually doing that L over H calculation also. So we'd have to put at least a 3-ton chain fall in this leg, minimum, to meet our requirements. But what happens if we do end up having to shorten this up? So the angles may become bigger, but we take a greater share of the load as the center of gravity moves closer to it. So we may be better off, a 3-ton may be a little too small, we may have to go to a 5-ton just to make sure it's covered. Now, on the other side, we have that same, another formula, tension in sling 2. So now we can calculate this one. Let's say we couldn't put the chain fall over here, but we could put it over here. So what we're going to do is use the same numbers. We're just going to use them in a slightly different formula. So we have our load times D1 of 104 times S1 of 72 divided by my height of 60, and in parentheses D1 plus D2, which is 104 plus 40. And we do the math and run it down. This sling is seeing 4.33 ton of force. So again, we're only picking up 5 ton. We've already determined this one may have to have a 5-ton chain fall on it. And this one also would have to have a 5-ton chain fall. Anytime you use slings at an angle, the forces on each sling will always be greater than the total weight of the load itself. They're always going to be higher. And so what people get confused with, well, I look at a sling, I'm picking 5 tons, so I'll put a 2.5-ton sling here and a 2.5-ton sling here, and I'm good to go. Not the case. You've got to make sure that you do it correctly. The other thing is, when you buy slings that are in bridles, they will come tagged with a capacity based on a certain angle. And normally that angle, we're going to put on there probably 3. It'll be at 60 and 45 and 30 possibly. But we normally, as you are the rigger, what you have to do is, if you're going to load them at any angle other than what's on that tag, you've got to do the math and do the calculations to make sure it's loaded correctly. And just to show you how bad things can go, let's take a look at this one. Here we're going to try to pick up this little block. So if you think it will take 1 ton to lift that block, raise your hand. Okay, I got 4 you say 1 ton. If it's 2 ton, raise your hand. How many you want to say 3 ton? How many want to say 4 ton? How many want to say 5 ton? Well, in order to pull on that arrow, to lift that 1 ton block, you have to pull a little over 1 ton. So we're going to go with 1 ton to overcome bearing frictions and stuff. And you just got to go like just a hair over to get it to come off the ground. So we have 1 ton. Next question. What load is on this shackle? How many want to say 1 ton is on that shackle? Raise your hand. Okay, I got 1 of you. 2. Okay, 4. All right, how many say 2 ton is on that shackle? Okay, how about 3 ton? 4 ton? 5 ton? So not everybody's voting, so nobody else wants to go out on a limb. Well, the correct answer is 2 tons of force on that shackle. You got 1 ton here and 1 ton here, total of 2 ton on the shackle. Next question is, what's the vertical share of the load on this roof truss? What vertical load is on here? What vertical load is on here? How many want to say 1 ton vertical load on each truss? Okay. How many say 2 ton on each truss of vertical load? Three ton? 4 ton? Okay. And 5 ton. Okay, well, if we have 2 tons of load on this shackle right here, then we split it. And each sling here is 10 foot long. That means we're equidistant to the center of gravity. This truss is seeing 1 ton, and this truss is seeing 1 ton. Now here's the big question. We've got each sling seeing a vertical force, or each truss seeing a vertical force of 1 ton. What is the force on the sling? What's the sling tension? And remember beforehand I said, okay, how many, how do you calculate that? And we use that L over H calculation, our sling length divided by height, and you multiply that times the share of the load. So here we have 1 ton share of the load on each truss. Our slings are 10 foot long, and our drop is 2 foot. So how many would say there's 1 ton of tension in the sling? By show of hands. Okay, nobody. Good. 2 ton? 3 ton? 4 ton? 5 ton? And 5 ton is the correct answer. So we have the 10 divided by 2 is 5, times 1 ton share of the load. This sling is seeing 5 tons of force here and 5 tons of force here. This is how things go bad very quickly if you don't do the math correctly. And you can see as we progress through, you've got to have the right answer at the very beginning in order to get the right answer at the end. If you make one mistake along the way, you can get yourself in trouble. So this is how important it is to do this. I actually showed this to a group of maintenance mechanics, 25 guys in the room, and all 25 guys go, oh crap. It turned out they'd done something similar with a 3-ton load, and it turned out that they had bent the roof trusses in the building. It cost the company a pretty penny to go in there and get the re-engineer and correct and modify and beef up the trusses to keep them from pulling the whole building down. So you can get yourself in trouble very quickly with sling tensions. Now this is, like I say, a quick overview of sling tensions. It's hopefully you've gotten something out of this today. Keep in mind, we do have but I've had no questions pop up, but if you have any questions, feel free to pop them in now. And keep in mind, we have 2 more sessions coming up on next week. June 1st is understanding the shackle, and June 8th is capability of the hook. Some of these pieces of hardware are misunderstood of how bad you can get in trouble and cause problems if you don't load them correctly. And then also running out for the next little bit, we still have a sale going on nylon slings. Buy 3, get 1 free of standard stock slings. So you should avail yourselves of that and get yourself ready now that everybody's starting to go back to work. And with that, I will hang around if anybody has any questions. And again, here's my contact information. I helped you out a little bit. I hope you learned something. And I thank you very much for participating with us today. Have a great day. We're going to go down here to question number 2.